We are continuing on our Statistics OER course, Unit 6, where we are learning about the central limit theorem. In this video, we will do some applications that use the central limit theorem. In the Intro to Statistics OpenStax book, this is section 7.3, using the central limit theorem. And in the Lumen Intro Statistics Corequisite book, this is module 7, and again we will be doing the central limit theorem. We will need Art of Stat apps, and especially the normal distribution app. So go to artofstat.com and you can use that. So let's try to remember. The central limit theorem said that when the sample size of a population increases and becomes greater than 30, then the mean of the samples, the means of the samples of the same size, n, will follow a normal distribution, and regardless of the underlying distribution of the population. And so will the sums of the x values of the variable for the whole sample. So if you are being asked to find the probability or percentile for some individual value of the variable, you are going to use the distribution of the variable, and then you will try to, based on that distribution of the variable, to answer the question. But if you are being asked to find probability of percentiles for the mean or the sum, and you have a sample that is greater than or equal to 30, then you can use the central limit theorem and a normal distribution. Remember, if you are looking for an individual probability or percentile for individual values of a variable, you have to use the distribution of the variable. You cannot use the normal distribution if the distribution of the variable is not normal. But regardless of the distribution of the variable, if your sample size is greater than or equal to 30, then the mean of the sample or the sum of the data values in the sample will follow a normal distribution compared to other means and other sums. The law of large numbers says that if you take samples of larger and larger size from any population, then the mean x bar of the sample tends to get closer to mu. From the central limit theorem, we know that as n increases, the sample means will follow a normal distribution with mean equal to the mean of the variable x and standard error equal to the standard deviation of x divided by the square root of n. And as n increases, the denominator square root of n will increase, and that means that the standard error decreases. The standard error is the spread of the distribution of the means about the mean of the means. This means that the sample mean stays very close to the population mean as n increases. And we say that x bar approaches mu as n gets larger. So let's try to solve some problems regarding this. We have a study. It involves stress for students on a college campus, and the stress scores follow a uniform distribution. So the variable has a uniform distribution. The lowest value is 1 and the highest value is 5. So from our formulas, the mean of that uniform distribution will be the average of the lowest plus the highest divided by 2, which is 3. And the standard deviation will be the square root of highest minus the lowest squared divided by 12, which is 2 divided by square root of 3 if you simplify the fraction, and that is approximately 1.1547. So if we have a sample of 75 students, the sample size is greater than or equal to 30, and therefore the mean will follow a normal distribution with mean equal to 3 and standard deviation or standard error equal to sigma divided by the square root of 75, which comes out to be 3 for the mean and 2/15 for the standard deviation. And the sums, so that will be for the mean, and the sums will follow a distribution that is also going to be normal because the sample size is greater than or equal to 30, and the mean of that will be mu times n, so 3 times 75, and the standard deviation will be standard deviation of the variable times the square root of n, so 2 square root of 3 times the square root of 75. This comes out to be 225 for the mean and 10 for the standard deviation of the sums. In our Lumen OER course, the final exam formula page includes these formulas. So here you can see the distribution of the sample means follows a normal distribution with mean, the mean of your variable, and standard deviation sigma divided by the square root of n. And the distribution of the sums also follows a normal distribution with mean n times the mean of the variable and standard deviation sigma times the square root of n. Now these assume that you have a sample size n greater than or equal to 30. Otherwise, you will not be following exactly a normal distribution. You will have to do other approximations that we will discuss later in this class. So the questions that we are given here are asking us to answer to find probabilities that the mean stress score for the 75 students is less than 2 and the 90th percentile for the mean stress score. And here I have already sketched the normal distribution for the mean, which is has an average in the middle of 3 and a standard deviation of approximately 2/15, 1.3 repeating, 0.13 repeating. So every tick mark is 0.13 repeating, and if it is a normal distribution, I go 3 tick marks to the right and 3 tick marks to the left for the first 2 questions. Remember that I have to label my axis to indicate what these values represent, and the values represent the mean stress score for a sample size of n equal to 75. So in Art of Stat, I want to fix the mean to be 3, and remember Art of Stat doesn't take an expression, so I'm gonna do as many decimals as I can just so that I have a good accuracy. And they are asking us to find the probability that the mean stress score of the 75 students will be less than 2. So 2 is somewhere here, and less than 2 will be over here. We expect this probability to be super small. 2 is really far away from the mean of 3. So I will do lower tail. The value of x I want it to be 2, and it will give me a probability I made a mistake here with my standard deviation. It is supposed to be 0.1333 repeating. That's what 2/15 is equal to. So again, lower tail, value of x to be 2. As you can see, 2 is extremely far away from this curve. I was expecting a probability to be very small. So for our purposes, we will round to the nearest 4, even 5 decimal digit. this is approximately 0. The 90th percentile for the mean stress score. So they are asking us to find what's the probability the mean being less than some answer, which is the 90th percentile, P90, and that probability has to equal 90% or 0.90. So we expect this to be between 2 and 3 standard deviations. We will find out what that value is in this area that is now shaded yellow will be 90% of the total 100% of the area under the curve. So let's find that. In Art of Stat, I need to be in the Find Percentile Quantile tab. I do want a lower tail. I want the probability in percent to be 90%, and that value is 3.171. So here P90 is approximately 3.171. That's again a score or stress score from 1 to 5. Questions 3 and 4 are asking us to find probabilities for the total of the 75 stress scores and the 90th percentile for the total of the 75 stress scores, and that is the sum. Again, the sum will follow a normal distribution with mean n times the mean of the variable and standard deviation square root of n times the standard deviation of the variable. The mean is 225. This is a normal distribution, so I only need 3 tick marks to the right and 3 tick marks to the left. Every tick mark is a length of 10 units. The label for the x-axis is the sum of the stress scores in the sample of 75 students. What's the probability that the total will be less than 200? So what's the probability sigma x less than 200 is the first question. So I'm going to go in Art of Stat. I will go under Find Probability, change my mean to 225, change the standard deviation to a 10. I need the probability in the lower tail, and I want this to be 200. So 200 is between 3 standard deviations and 2 standard deviations below the mean. So between the values of 195 and 205, this is where 200 is. So I'm looking for the probability here in the lower tail, and that probability, according to my technology, is 0.621% or 0.00621 if they want it as a decimal. The 90th percentile for the total stress scores, it will be again some value between 1 standard deviation above the mean and 2 standard deviations above the mean. The probability in the lower tail has to be 90% and 10% above in the tail that I'm not gonna shade. So this thing has to be 90%. They are asking me the probability that the sum of x being less than this value that I'm trying to find, which is the 90th percentile, will be equal to 0.9 or 90%. And I'm gonna do that again in Art of Stat. So under Find Percentile Quantile, the mean is 225, the standard deviation is 10. I'm looking for the lower tail, 90% probability, and the answer will be for the sum, 237.82. One more example in the applications of how to use the central limit theorem. According to Boeing, data, the 757 airliner carries 200 passengers and has doors with a mean height of 72 inches. Assume for a certain population of men, we have a mean of 69 inches and a standard deviation sigma of 2.8 inches. And what mean doorway height would allow 95% of men to enter the aircraft without bending? And assume that half of the 200 passengers are men. What mean doorway height satisfies the condition that there is a 0.95 probability that this height is greater than the mean height of the 100 men? So, in the first question, we are talking about 95% of individual men usually heights of men for populations are normally distributed. We don't expect heights to have some kind of uniform distribution or any other kind of distribution since it's a natural phenomenon. So here we will assume that the individuals also follow a normal distribution with a mean of 69 and a standard deviation of 2.8, and we will sketch our curve here as a normal curve. And this will be men's height in inches. And the mean will be 69, and every tick mark will be 2.8. And they are basically asking us for the 95th percentile, this question, because it says what mean doorway height would allow 95% of men to enter the aircraft without bending. So we would like 95% of the population to be able to pass through a particular height. And that height will be somewhere here between the 1 standard deviation and 2 standard deviations above the mean, so that the area below will be 95% of the men who have a distribution with a mean of 69 and a standard deviation of 2.8. And we want to know what will the height of the door be so that 95% can go without bending. So the question is, what's the probability that x will be less than the p95? And that obviously probability will be 95% or 0.95. So I'm looking for a percentile quantile, the 95th percentile in more specifically. So I'm going to stay in the find percentile quantile. I'm going to change the mean to be 69.0. And I'm going to change the standard deviation to be 2.8. And I'm going to ask for the lower tail in the 95th percentile. So the height of the door will be 73.6 inches. And that will allow 95% of the individual men to go under the door. The next question says that we now have a sample, and our sample has 200 men. Well, actually, we have 200 passengers, but the men are 100. So half of the 200 will be men. So we have a sample of n equal 100. And now they are asking us what should the mean doorway be to satisfy the condition that there are there is a 95% probability that the mean height of the 100 men will make it under that door. So here we are looking for the mean distribution, the distribution of the sample mean of 100 men. The sample mean will follow a normal distribution since the sample is large enough that has a mean the same as the variable 69.0 and a standard deviation 2.8 divided by the square root of 100, which is 0.28. So the x bar follows a normal distribution with a mean of 69 and a standard deviation of 0.28. So now this normal distribution will have the mean height of a sample of 100 men in inches. And that mean will still be here at 69, but the spread is no longer 2.8 for every tick mark, but it is 0.28 for every tick mark. So I'm going to still do 3 tick marks to the right and 3 tick marks to the left. But the values will be 69.28, 69.56, 69.84 to the right, and to the left, going down by 0.28, 68.72, 68.44, and 68.16. Now, I do want to draw your attention here to the fact that once we have determined the sample size, our bell-shaped curve is very, very narrow. So we expand it so that we can see it. The farthest it goes is less than 1 unit. 69.84 to the right, 0.84 to the right, and 0.84 to the left. So it actually has become very, very narrow, and that's the whole purpose of the central limit theorem and the law of large numbers that says that as your sample size increases, you do not deviate, your sample mean does not deviate from the population mean of the variable too much. You do stay really, really close. So this particular curve has now been expanded here so that I can see a little better. And they are asking me again for the 95th percentile, which will be between 1 standard deviation and 2 standard deviations above the mean. And I'm looking for this range of values that have the property that they are 95% of those sample means will be less than or equal to the particular value that I'm looking for. So this is the probability of the x bar to be less than this P95, which will have probability 95%, and the P95 for that will equal to, and I'm going to use my technology to find it. So I have a mean of 69, but now I have a standard deviation of 0.28. And I'm looking for the 95th percentile, which is 69.46 or 69.5 inches. So 76.6 inches needs to be the height of the doorway so that 95% of individual men can go through. 69.5 inches will be the height of the doorway so that the average of 100 men for every trip will be below that 69.5. Assuming that things will look kind of normal even within the 100 people in each flight, we will assume that this is, if it's normal, the mean and the median are the same. So we will say that half of these men will actually make it under the door without bending.